Hey, good afternoon. Welcome in the session with Geoffrey Négiar, Beyond Next Steps Prediction, Open Challenges for Time Series, and so on, really. Geoffrey is the co-founder and CEO of the forecasting company. The company builds foundation models for time series data and systems for cleaning with the temporal data and all their cases to improve planning for the world-leading organization. He previously built forecasting system at Amazon, AWS?
No, retail.
Retail, okay.
Yes.
At Amazon, Bloomberg, and Shift Technology, and worked on machine learning research at Google. Please, up to you.
Thank you, Mohsen. Thanks for the introduction. Hi, everyone. So we're going to talk about open challenges for time series foundation models. You might be familiar with foundation models, otherwise you would probably not be here. They have shown tremendous promise in this field and are already changing the practice of forecasting quite a lot, but there's still many open challenges. So I'll start by telling you a bit more about us and what we do at the forecasting company and what we've built so far, and the vision and for the next steps to make foundation models for forecasting actually production ready and to be able to handle the full stack of forecasting and all the different use cases that we see in practice. So a little bit about me, but Mohsen already said most of this, so I'll probably skip most of it. But previously, I did my PhD at UC Berkeley, working on hard constraints for machine learning. Hard constraints is something that shows up in decision-making all the time. Through dealing with hard constraints, that was my entry point to forecasting. Because most of the time, when you have a decision-making problem, the inputs to that optimization problem are future forecasts. So through that, I was working, as Mohsen said, with Amazon Forecasting Science, at Scott, at Bloomberg, at Shift Technology on different forecasting problems. And that led to, starting with Joachim, who's right there, to the creation of the forecasting company a couple of years ago. This is our team. You might have bumped into a few people here at the conference. Almost everyone is here, except Huikan, who unfortunately only got her visa for Canada yesterday, and so therefore could not attend. But everyone else is around, so if you see any people with this t-shirt or another color of it, you can bump into them and you can ask them questions. Couple of sentences here. So we're a mix of people from the forecasting industry, applied in different companies, but also from machine learning applied research, from companies like JP Morgan, Polymathic, and a mix of like machine learning research and different kinds of research. All of us come together to build forecasting systems through the foundation model approach and systems around that. Forecasting 2 years ago, but actually it's also true today in many, many places. Usually people built and continue to build a single model per dataset or per use case. Often it's tuned by an expert, many of which, the leading ones at least, are at this conference this week. And building those systems or adding use cases and handling the whole possibility or the whole business use cases that an organization needs is usually gated by time and expertise. So, statistical models like ARIMA ETS theta, or models like light GBMs, trees, etc., are strong actually in practice, but they're very bespoke and they're hard to scale to millions of series and especially to many, many different use cases. This is the promise of foundation models, which is something that actually does not come from the time series literature at the beginning, at least. It comes from language first. Well, vision and language are the two main areas where these appeared. The recipe is always kind of the same, meaning that you want to train on massive amounts of data for what people call a pre-training objective, which is usually also what people call self-supervised, meaning you don't need labels to train this first iteration of a model. For language, that means trillions of tokens on the web, so just texts, that you train to predict the next token, the next word or the next sentence in the text. This is the pre-training objective. There is what after came to be known as post-training, where you actually steer those models towards behaviors or capabilities that you think are interesting, like writing code or solving different kind of medical problems, et cetera, which is not just pre-training. In vision, the pre-training task is billions of images. You just randomly mask parts of the image, and you pre-train to fill in those mask patches. Of course, again, post-training exists, where maybe you want to do Q&A on a question on an image, or you want to do different types of tasks on these images. For time series, we're still at the pre-training phase, meaning that post-training for time series is not something that has clearly appeared yet in the literature, and it's still unclear what it means. So what people do now, and what we do, for instance, is we take billions of time series, both real and simulated, and we'll train to predict either the next patch or a patch in the future. It doesn't have to be right away, because often in forecasting we have long lead times, actually. So you don't always just want to predict the next step, but you want to predict some patches in the future or some values in the future for your time series. Single model, again, any kind of time series, 0 shots. The same recipe works for pre-training, but there's still a lot of questions, especially around the specificities of time series. And we'll get into that later, but the current ideas around pre-training are not necessarily capturing everything that we need to have a good time series model. So we'll be talking about that a bit. What's a time series foundation model end-to-end? It's billions of time series from many different sectors. So think retail, energy, web, finance, economics, sensors, synthetic data from simulators of all kinds that you pre-train or compress into a single model using this predict the next or a future patch objective, fully self-supervised. You don't need labeling, you don't need human annotation, anything like that. Probabilistic forecasting, so these are the loss functions that we optimize for this, and that gives you a model that is capable of zero-shot forecasting for any new single series. The promise is that forecasting becomes instant is just an API call, similar as you would have for a language model or a vision model or a video model or a speech model. All of those are kind of solved and well, not solved, but they do this, right? And makes a new forecasting project API calls and not a full project that require tuning, expertise, et cetera, et cetera. What does a zero-shot forecast look like? This is one example on real data, actually. So you put the history. This is univariate example, and then you'll produce a probabilistic forecast. And here you can see it actually matches pretty well the real data. The real data is grayed out. The forecast is in green and shaded green. So again, no training on this series. You just get history in and the full predictive distribution out. There's been a bunch of pre-trained time series foundation models. These are a few examples. They're pre-trained. All of them are pre-trained on large heterogeneous corpora. There is a form of convergence on capabilities and architectures that have happened over the last 2 years. Usually, people measure zero-shot accuracy across these domains, and these models now often match and sometimes beat task-specific statistical methods. It always depends on how much effort you put into tuning the statistical methods so far. But for lightweight tuning, let's say, these foundation models are an extremely strong baseline that you can use now. There's 100+ models on a benchmark called GIFT-eval, which is kind of the benchmark that most people use in this field that covers, there's a total of 97 data sets across different frequencies, domains, different sources, of course, and different horizon lengths, et cetera, et cetera. Model size so far in this field does not really predict accuracy. There's one very recent piece of work by our friends at Datadog that show that when they scale the model size, they can actually get better accuracy, which is the same that happened in text. But it's still a fuzzy kind of statement in a way, because the relationship between scaling the data and scaling the models is not entirely clear yet, as it was for large language models. So you see here, so our model actually is the one right here in green. So it's doing pretty well at a pretty small size, 100 million parameters. 100 million parameters for forecasting practitioners can seem like a crazy amount, actually, but for deep learning models, it's quite small. Some of the bigger models here, the total one in particular, is 2.5 billion parameters, which starts to require like specific infrastructure to run. It's not that easy to directly run it on your laptop, but this model, like this size, you can actually run on your laptop fine. These here are supervised or previous generation models, let's say. Deep learning supervised models and classical statistical. These are the results reported in the benchmark. I wouldn't fully trust the results here in the sense that those models or those learning algorithms were not fully tuned by experts when they reported the results. But for people who are not full experts, you can see that the foundation models actually beats these statistical and supervised models. I'll say a few words on what we've built before moving on to challenges in the field. So we've just released this model called T0 Alpha, which is 100 million parameters roughly, a zero-shot history and distribution out. It's a quantile regressor, essentially. It's multivariate, both input and output. So it can take actually multiple targets in the inputs. It can produce multiple targets in the outputs. It also takes both historical and future covariates. We've built the architecture around this, and we'll be talking a little bit more about that later. It's competitive on GIF-TVAL. It's not state-of-the-art fully yet. That's why we call it T0 Alpha. But it does beat models up to 7 times its size, and it's within stone-throwing distance from the state-of-the-art. And this we built actually with a team of 5 researchers at the forecasting company over the last year, let's say. So as a small startup, we actually don't have access to data like Amazon, Salesforce, or Datadog does. The foundation models that they trained, of course, uses their proprietary data. We don't. So the way we do this is by blending real data with simulation data and proprietary simulators that we have internally. And this is an important thing now and going forward in the field, because these simulators, so these foundation models are really a compression of data and your beliefs around the world. And building these simulators right and throwing that into the foundation model is the way to move forward. And that is what encodes kind of the world and your hypothesis around the world. We use 4 different simulator families for now. Statistical, anything around Gaussian processes, structural causal models, agent-based and physical. Actually, this is 5 simulator families. So agent-based models and physical simulation models. Simulation is how we also deal with covariates, how possibly in the future we will deal with interventions and hierarchy, things that I'll be talking about later that are actually very important challenges to put these forecasting models, these foundation models for forecasting in production. Our bet is that simulators good enough to train on is what actually people are calling now world models, and what people are building whole companies upon now. A world model being something that encodes the state of the world and also how the world reacts to certain operations or interventions or actions upon it. So our argument is that actually forecasting foundation models done right is a form of a world model that learns in context from the data you provide to it. So we're designing the whole model and our systems around the use cases and the business use cases that we see in practice, not just around the benchmarks or public benchmarks that we see. In the benchmarks, so you're optimizing a very specific loss function that's very often this univariate loss that is not actually what people care about in practice. On Retrocast, so this is our platform and system, we encode or we have directly available the hierarchies, the correlations, all the structure in the customer's data as a first-class citizen, which is not the case in current benchmarks in foundation model space. So this whole interface describes the business logic, not just a tensor, not just numbers, as the usual interfaces of other models do. This is an example here of a request to our API. So you just give what the data source is, probably a list of Parquet files or CSVs, and then you show the schema of your data. So, of course, dates, usually, identifiers, which can be SKUs or other things, and the sales, which is a target here. And you say that, of course, sales is something that you aggregate by summing, not by averaging like a price or something like that. Once you've encoded the schema once, so this single API call actually performs a full backtest that will produce forecasts every 2 weeks with a length of forecast every 3-week horizon, and will return the full results for our model and other models, because we've abstracted that away as well, directly in a single API call. But this API call is really describing the data and describing the use case through these hierarchies, etc. This selector, for instance, actually shows that we want the backtest to happen at the product family level and not at the SKU level. So implicitly, actually, it will aggregate up and produce the forecast at the right level. So if you want to take 1 minute, you can scan this QR code right now and make your first forecast on your phone using our model live. So I'll give a minute for people to actually do that. So you don't need to log in. It's really just you're going to appear on the picture. There's 4 or 5 example data sets or example time series. And whenever you click on it, you'll be able to make a forecast immediately. And this is one part of the power of these foundation models, is the interactivity that they allow. So whereas before you would have to fit a model, take the data, put it into a machine learning pipeline or a statistical pipeline before you could get your first forecast, here it's really point and click and immediately get a forecast. The same way now people are getting used to interacting with large language models. Which means you can also run experiments by changing covariates or doing interventions or whatever directly live and get a good intuition and kind of do a human sensitivity analysis almost. You could, of course, do this computationally and get more quantitative results, but even for building intuition for stakeholders or less technical folks, they can see the forecast change whenever they change the inputs, which really helps people build intuition around these models. So, now that we've talked a little bit of what we do, let's talk about what's next for the field and what challenges, what are foundation models not able to solve right now, and how to make them better. So why do we forecast, right? Everyone here knows that forecasts are a means. They're not an end in themselves. Usually, forecasts allow for a decision, right? Either that the forecaster themselves take, or a business user, or an automated system for inventory replenishment or management. All the time, these forecasts are inputs for better decisions. So this is really what we want when we are building these foundation models for forecasting, as we are for the rest of forecasting. We want to optimize the decision. Sometimes that means optimizing the loop end-to-end again, but often it's a human deciding. So you need a model that you can plan against, actually. A model that gives you the sensitivity and the interaction to be able to justify the decisions that you're making in the world. There's a lot of gaps. One of them is that benchmarks, in particular, reward the diagonal, meaning that it's only the marginal MAE or MSE or CRPS, one series at a time. Decisions actually need the joint distribution. So forecasts, should aggregate, reconcile, and answer these what-if questions. One example here for stores, of course, geography, product. So these different hierarchies we need to aggregate and deal with. And we need the joint distribution, actually, over everything if we want to make a decision from the top level to the bottom level. Current foundation models are not at all able to do this. These are kind of broadly the categories of open challenges that I want to talk about. First of all is structure and modeling this joint distribution, right? Very often, it's not just a single number that you're trying to forecast, but it's really either it's a top-level aggregate of something else and many things evolving together, right? The GDP is actually the aggregate of all the firms in a country. Your sales are the aggregate number of all the SKUs, all the different stores, etc., in your network. For energy, the grid is, of course, on a network as well. So you usually want to have this joint distribution modeling to be able to handle, well, to make better decisions. And this joint distribution cuts up in multiple aspects. One is covariate integration, of course, so handling, let's say, weather for energy forecasting, of course, or promotions or things like that. Two is hierarchical coherence that I've mentioned a few times already. Three is temporal aggregation, because very often, let's say your data is at the daily level, but then depending on the decision or depending on the use case, you might be making forecasts at the weekly level or monthly level or quarterly level, and you want all of these forecasts and decision to match again. The same way the hierarchical coherence over, let's say, the geography axis, we also want this in the temporal axis. And again, multi-frequency and irregular data, in a lot of cases, the covariates or the targets don't have matching frequencies, right? Again, the GDP example, you have numbers every quarter, let's say. But actually, in practice, you might have data that's monthly or weekly that you can leverage to make these higher level forecasts. So how do you align things, and how do you make sure that the model can handle all of this? Causality, of course, so things like promotions, pricing, but any kind of intervention for the user. These are things that are important and that are not handled currently by time series forecasting models, by foundation models. And the other part is context, which is rather similar to the large language model side of things, where given the model is zero shot and the output changes depending on the inputs, you want to be able to optimize the context that you feed into the model to get the right outputs, to get the right forecasts. So I'll be diving a little bit more into detail on each and every one of these. So first of all, structure, covariate integration, you all know these examples. But if you have a promotion that's coming, for instance, here, the discount is known in advance, actually. So similar to a booking or something like that, you actually know something in advance. You decided at some point for another point, and you want to be able to measure that impact or the lift. Covariates are ragged in the sense that because of these foundation models, because of their flexibility, you don't have to have a single data schema, actually, for all the data that you plug into it. So perhaps one region will have certain covariates like temperature, let's say for energy, but in other regions, temperature is less important because it doesn't fluctuate as much, or because behaviors don't matter so much, are based on temperature. So this is, yeah, these are tough, and also especially because you might not actually have examples in the past of the same time series where this promotion or this covariate actually matters. So you might want to optimize your context differently, and this is tied to the cold start or warm start that I'll talk about a little bit after. Most time series foundation models ignore covariates right now, even the leading ones. So models like TimesFM are purely univariate, for instance, and you cannot actually feed them covariates. More recently, Chronos 2 and a few others have been able to deal with covariates. This is something we was utmost importance for us when we built T0, so that's why even the first version of our model actually can leverage covariates, both historical and future. Hierarchical coherence. So of course, you've probably seen these plots already. If you have different stores or different network or a graph of or a network of grids in the energy sector or something like that, you need to forecast everything jointly, right? And if you don't, so these are probabilistic forecasts. So since you're providing quantiles for every time series, you cannot add up these quantiles. Adding quantiles without coupling them just doesn't make sense and will not give you the quantile of the sum. So being able to model this in the time series again is necessary for these types of problems, and this is not something that exists today. There are ways, again, to do reconciliation post hoc, like min-t, but these are, you actually need to fit an optimization problem for the specific task. What we would like for the foundation models to be actually foundational is to be able to deliver this coupling directly zero shot in one go, which is not possible if these models are trained just for marginal quantile regression. Again, temporal aggregation, I'll skip over this one maybe a little bit because it's quite similar to the previous one with hierarchical modeling. But essentially, yeah, the same holds. When you have marginal quantiles at every time step, let's say every day, that does not give you the quantiles every week. And you'll have a gap if you just sum up these quantiles. And oftentimes, this will under-forecast, actually, and not be satisfying for the use case. Things around multi-frequency and irregular data, different covariates or different time series that are relevant to predict each other, or one that's relevant to predict another one, might not have the same sampling. Some might be more transactional, some might be news that appears kind of randomly at different dates that's not aligned every week with your sales data, for instance. So again, being able to handle this is key for the foundation models to actually be useful in practice. Causality. This is what allows you to do interventions and make decisions through, let's say, the standard examples are promotions or discounts or things like that. This allows users to answer what if. What if we did this? How would my target change? This requires do calculus, and the only way to do this actually is to have a causal model, right? And how do we have a causal model here when we talk about foundation models? We have to train them on simulated data, where the simulators have this causal structure baked in. And once we do that, the model itself can capture causality. If we only train on observational data or real data, it's very hard to have this causal relationship because everything is conditional. It's not causal. So again, this really implies the requirements to have strong simulators to train these models on. And there's been some work on this, in particular do PFN and causal PFN, more in the tabular space, but that has not been transposed yet in the foundation models for time series space. Context optimization or context engineering. So things like cold or warm start. Of course, if you have a new product or new launch of a store or a new location or a new data center that you're building or new building itself for temperature management or something like that, you need to provide the correct context for the model. The model is not going to invent the structure of what you're trying to predict. So here, there's a few models, again, that are trying to do this via what's called in-context learning. In particular, Apollo PFN, Chronos 2 are the models in time series space, and our model, T0 Alpha, that can start to deal with this. But this is still at its infancy. One of the reasons is usually the time series are not aligned, right? The time series that you want to show as example are usually in the past, whereas your time series that you have a warm start for is happening now. So there might be a time gap between the two, and current models actually are really not good at handling this time gap. Just through the input and output, they usually need all the time series and all the context to be aligned and don't handle these gaps very well. And again, and retrieval is again around this context engineering or context optimization case. How do you choose for the warm start, for instance, what products or what examples are relevant for the specific task that you're trying to attain? In large language models, at the beginning, when they were focusing on the pre-training objective, there was this big problem of hallucinations, and the model would only have what it saw in the training phase in its memory, And RAG was the way to unlock it and to give it actually the full knowledge of the world, and also to allow the model to query itself, or write the queries that answer the questions that it needed for the specific task. There is very, very budding work in this space, but it's not clear yet, because most of the models, most of the work in this space is actually around pre-training and not post-training, and not tool use in the time series side of things. So this allows you to go kind of beyond cold start. Well, cold start, it's still the user that feeds in the context. Here with a retrieval augmented forecasting system, you would just be able to point it to a database or point it to the world, and it will actually pull in the relevant context itself to make those forecasts. Finally, multimodal context, which is very tied to the previous steps. If you want to do cold start or warm start, usually you want to tell the model, oh, actually this item is from this product category. It's how maybe I have a description, maybe I even have an image of the product. These are all things, this is something that people actually have in production with light GBM models or deep learning models that are tailored to a task. They do have this joint embedding of different modalities, but this doesn't exist really for foundation models in the time series space. But again, so to replace or to be competitive with production systems, we need that to be native to the foundation models in forecasting. There's another case that's interesting, which is this rare events case. So here, for instance, this is also a data set where there's simply closures every Christmas Day and every 1st of January. But say you have only like 4 or 5 years of data. This specific pattern, of course, similar to Black Friday or other yearly events like this, you only see them once a year. So in practice, you only have 4 or 5 data points in your whole objective function for this, right? And so what that means is when you use current foundation models, they completely gloss it over. Even if you give them the covariates of the closing, even if you put a Boolean indicator that the store is actually closed on that day, you still get a forecast that's kind of like this, and it doesn't at all capture these closing dates. This is, of course, a big problem. That's pretty obvious. And here, this, for me, in my perspective, is again an argument for this joint distribution. Because if you have the time series for a bunch of different stores or different items that all have this pattern, you can actually increase the data count or the sample count for these types of events. Whereas if you're only forecasting at the top level or at the level that you are forecasting at now, and not jointly forecasting at different levels or across different items, this does not get handled at all, and you get an incorrect forecast. So again, you need the joint forecasts, and you need the ability to have all of these inputs at once in the model. So these are the 3 threads. And the one diagnosis, or the one thing we're seeing here, the conclusion is none of these capabilities that are absolutely key for production models. If you talk to any practitioner that actually has models in production in the classical sense or non-foundational sense, actually can handle like these different things in some way if it's important in that system. But the foundation models are not able to handle these. None of these are actually solved by just scaling the number of parameters of the model. These are all structural problems of how we model the task itself. Right now, all the foundation models that are out there model the task as a next value prediction problem with quantile loss, marginal quantile loss. If you stay within that paradigm, none of these problems are solved. So again, like, what you really need to build is a world model, and a world model is not just this next token marginal forecast. A world model is something where you can predict a joint distribution, which means something you can sample from, something you can marginalize on certain variables, but not directly have to have marginals and only able to have this. So solving these is the frontier of foundation models right now. I think there's not that many teams or people who are thinking about it in this way of joint distribution because the benchmarks push the field in a specific direction. And the benchmarks are all looking and evaluating marginal quantile regression metrics, essentially. None of them actually look at joint distributions. None of them look at correlations between targets. None of them look at these, well, or only a few of them look at these warm start or cold start problems, but they're still, let's say, more niche. They're not the core metric or the core benchmark that people are optimizing when they're building in this field. The other thing is these benchmarks average over many cutoffs or forecast creation dates, and also over fixed horizons. So they never zoom into the events that matter, actually. So we'll never, for now, the main benchmarks in the field, they don't actually look at the metric over a Q4 spike or a holiday or a closure or something like that. And so the behavior at that specific point of interest that's extremely important for business use cases actually kind of gets averaged over inside the benchmark. And so right now, a lot of the benchmarks are strongly correlated, including the ones that have access to covariates like holidays or closures or things like that, like FevBench that came out not that long ago, just because the models gain more on that benchmark by being better like general time series forecasters and not better at actually handling this joint distribution of their covariates aspect. And so if we actually had something like an event zoomed metric where, in the benchmark you would have a specific number that says, okay, you are good at holidays and you are good at closures and things like that, that would actually push the field into solving these problems, which is not the case at the moment. The other thing is leaderboards should score the joint distribution. Can you actually sample consistent scenarios across series, right? Can you condition, do you know how two stores co-evolve over time? These are the important questions to make decisions, right? If you just have the marginal quantiles over each store, but there's a hidden factor that is the same, like they're both affected extremely by weather, for instance. These are things that do not show in the benchmarks and that people therefore don't optimize for. These better benchmarks, I think, right now matter more than better architectures for solving the existing benchmarks. So this is really, I highly encourage people in the field to work on these benchmarks aspects and to, especially for practitioners, for people in industry, to be able to encode what's important for you and for your business and for your stakeholders in these benchmarks that will be widely shared. Then the machine learning loop kind of kicks in. If you give machine learning practitioners a benchmark, they will optimize the hell out of it. And so you will solve the business use cases that you actually care about. But today, it's not exactly the case in this field for now. So open questions, this is still something I want to kind of leave you on, is overfitting. So of course there's this question of if there are benchmarks and people optimize the heck out of it, are we actually just overfitting the benchmarks? So there is a question there is, if we're actually training the models on significant amounts of synthetic data, can we still consider that we're overfitting the data, given that we've never seen it at all during training? Of course, there are these kind of meta overfitting problems, but it's still an interesting question of how does synthetic data, and especially when people think about backtesting over COVID, for instance. So if you've only fit your model in synthetic data, but maybe you've evaluated on benchmarks that are post-COVID or during COVID, would you have been able to forecast COVID or things like that at the time? It's really something that's not very clear. The other question is, what does it mean to post-train a time series model? And what does it mean to scale like test time compute? And what does it mean for now? Foundation models in time series, they use the same compute for all the forecasts. But in large language models, for instance, when a problem is harder, it'll use a lot more tokens to solve that problem. There's no equivalent of that currently in the time series forecasting literature. So that would be an interesting thing also to look at. And the other part, which is a really important part given all we've talked about, is what's the correct joint training objective? So if you actually want to do this world model and build a model that can do this joint modeling of many different things that are correlated or causally related, what is actually a joint training objective? And what is a good sampling scheme? Because if you have 200,000 or 10 million or 400 million SKUs in your platform like Amazon does, they have hundreds of millions of SKUs, how do you sample to be able to train a model that actually models the joint distribution over everything, right? This is a very open question, I think, and quite an interesting one to move in the direction of these world models. This is, again, call to the field. Benchmarks matter, and especially in the direction that machine learning is going these days, where things like auto research and loops that are semi-autonomous can actually improve benchmarks as long as the benchmarks are well made. I think more and more effort should actually be in the benchmark itself. What are the metrics? What is the data? What are the important parts of the data? How do we weight the metrics over the different parts of the data? Once we have that, the rest we can pretty much automate the improvement loop once we have this information. But we really need this information, and this is something that only practitioners and end users actually know and have through their experience. Classical forecasting has all of this. All the systems, well, the best systems in production actually answer all the questions in this talk, right? They have reconciliation, they have hierarchies, they have causality, depending on the use cases. And of course, there's still ongoing research there, but a lot of these things are solved in some way. So the foundation model field has a lot to learn from practitioners that have or continuously put in production these systems using the more classical methods that are tuned to a specific problem or a specific use case or a specific data set. And the question then is, how do we generalize and how do we make a single model that just like has all these capabilities and that we can ship to production? The last part is foundation models work on the objective that we gave them. So now this is pretty good actually for univariate quantile regression and things like that. The models work. Now we need to expand what it means to work so that we can actually put them in production for real systems. So the question there is, can we give them all the bells and whistles and cook that into a single model, single system that then we can put into production everywhere? That's pretty much it for me. If you have any questions, I'd be very grateful for them and very happy to take them. I think matching the best models practitioners build, like this is the main takeaway. It takes a lot more than scaling the models. It takes actually getting the problems right and getting the modeling right. And we can only do that if we have the right benchmarks. So this is really the one takeaway I want you to go back home with is please, as practitioners, and even as people who don't directly work on the foundation models themselves, you can still have an enormous impact in this field by working on the benchmarks and by putting all your knowledge that you've had through years of experience in this field into the structure and into these benchmarks. This would be incredibly helpful and would move this field forward by a lot. The other thing, of course, is T0 Alpha is free on Hugging Face, so you can download it and try it, and please give us feedback. Again, we can only push the models forward and the systems forward if we get this feedback and these benchmarks, so we're always eyes and ears open for that. And if you're interested in working on these types of challenges in any way, either as collaborators or full-time, please come and talk to us. We're always excited to have those conversations. Thank you.
Thank you, Geoffrey, for the That's a really great presentation. Thank you very much.
Thank you.
We have a little bit time really to take some questions, please.
Hi, I'm Alan King from IBM, and, well, retired. So we used a tiny time mixer. It's not really a transformer model. It does a lot of patching and mixing. And one of the things I was surprised about was it didn't report on residuals. So when we examined the residuals, we found that there was a lot of autocorrelation. So we found that we could get a much, much better forecast, if you will, by adjusting the residuals. And so my question is this something that's on your in your awareness and on your roadmap?
Yes. So actually, this is one of the reasons we built Retrocast, which is this little visualization app that we have, is to be able to look at the residuals and do these kind of deep dives. So yes, this is something we've seen also, where in some cases the residuals have patterns and have signals. And I think in particular, more on the covariates side, you can see that even if, for now, even with the models that can take covariates, even when you feed them the right covariates, you look at the residuals and you still see something that should be explained by the covariates, right? And so I think that this is something that the field still needs to work on so that the residuals are actually residuals, right? Meaning that they've removed all the information from the input that you give the model. Yeah. Does that answer your question? Yeah.
Laurent, you have a question?
Yeah. Thanks a lot, Jeff, for this very clear and nice presentation. So when you talk about multivariate model, I would like to do maybe the analogy with macroeconometrics. If I imagine, for example, a multivariate model that is a small structural VAR, we have something in mind with, I don't know, 6, 7 variables. Is it a size that is compatible with what you mean? Yes. Or can we go above this size and think about large VR? Or
yes.
Is there an issue as related to the size of the multivariate system?
There is. I think the models so far are capped on the number of covariates that they've pretty much seen during training. And so currently, the order of magnitude that they've seen during training is usually in the few tens or less than 100, let's say, right? But anything up to between 50 and 100, depending on the models and depending on the training procedure, usually models can handle-ish. But again, none of the models so far that exist are outstandingly great at doing multivariate forecasting. And the other part is, because they only do this marginal quantiles, even if you have 6 or 7 covariates, or even if you have 50, or not covariates, but targets, right, multivariate targets, you still don't know the coupling, right? Which is a big problem, especially in macroeconomics, where you want the co-evolution between, let's say, interest rates and GDP and and unemployment or things like that. If you only have the marginal quantiles, what are you going to do with it actually?
So it means that you do not deal with quantiles in this case.
Sorry?
It means that when you go multivariate,
yes,
you continue to use quantiles, or?
Yeah, so all the current models that exist,
they use quantiles, right?
They use marginal quantiles or marginal samples, marginal distributions, but none of them actually natively handle joint distributions at all. Yeah, and so I mean, one idea there is, instead of producing quantiles, which is computationally much more efficient, and which is why the field actually went in this direction, I think we should be producing samples actually, and we should be or distributions that are sampleable in a correlated way. So either through factor models or coupling or like copulas, something like that. But all of this structure needs to be built into the model itself, and it needs to be able to adapt to the input, meaning that if you give it 5 variables, it should give you a coupled joint distribution of those 5 variables, but if you added a 6th one, it should also give you a coupled distribution over the 6 variables, right? And it should be able to do this on the fly without having to do a post hoc coupling mechanism or fitting a copula or something like that. This should be directly native in the model. And this is something that doesn't exist so far.
Yeah. So it means that the shape of the copula is part of the assumption of the model.
The shape of the copula should match the input, and it should be kind of model agnostic. It should be input dependent, right? In the sense that if you have 10 variables, you should have an output that is, correlated samples over those 10 variables. But if you have 100, it should be coupled samples over 100 variables. But it shouldn't be a hypothesis of the model that you always have 10 variables or always 15, because then it's not a foundation model anymore. It cannot adapt to any kind of data that you plug into it. Does that make sense? Yes?
Thank you, Laurent. We have another question here.
Hi, thank you. I'm just wondering if you are mining the time series we provide to you via the API for future training.
This is opt-in only. Yeah.
Clear. Yeah.
Thank you. Great talk. I was curious, a lot of the stuff that you were saying, like the need for due calculus and the sampling needs and the need for the joint instead of the marginal, sounds like very a Bayesian approach. And I'm a big Bayesian guy. And so just wondering are you guys thinking of it in that Bayesian lens, or how are you guys approaching this problem? Because it sounds to me, I hear all my little fun terms that I like. But.
Yes. I think the way we're approaching it is the model itself is a compression of different simulators or different data distributions that you plug into it. And so we are thinking of Bayesian structure, but more in the data generation process for the training data, and less so for the architecture of the model itself. Although, especially for coupling, you could imagine a model, and I've worked on this previously when I was at Amazon, actually. I had a paper that I presented at ISF last year about this, was if you have a factor model, for instance, a probabilistic factor model, you might have a transformer model that actually outputs the parameters for this factor model. And so you can, through that kind of modeling, actually get coupling between the samples and things like that, right? So, but right now the way we're thinking about it is more the simulation and the training data in the universe that we show to the model has a lot of structure. Has this causal structure that we know because, if we've built a simulator, we control absolutely everything. And then, because transformers are really good at matching patterns, then when you show it real data, internally in the representation of the transformer, it kind of maps it to some form of internal causal model. But you'll never see it explicitly, right? And so you'll just get this input-output relationship that you have with LLMs and transformers and black boxes like this. But because of the training procedure and the data that you've trained it on, it has this kind of Bayesian way of thinking about things. That's kind of the way we conceive it.
Any other question? Okay. Thank you again, Geoffrey.
Thank you very much. Thanks for...
Just a reminder, we have a member, the IAF member, meeting in a few minutes, I think in 15 minutes.
All right. Thank you very much.